Have you ever wondered what would happen if the sun suddenly erupted and sent a massive blast of plasma and magnetic fields towards the Earth? Well,
Something
you don't.
extraordinary is happening on the surface of the sun right now. A region of intense magnetic activity has unleashed one of the most powerful eruptions our star is capable of producing, a coronal mass ejection that has sent billions of tons of electrically charged plasma hurtling through space at millions of kilometers per hour, and it is aimed directly at Earth. Before you worry, let's be clear about something. This is not a catastrophe. This is not the end of the world. In fact, for most people on the planet, this event is going to be one of the most visually spectacular natural phenomena they have ever had the opportunity to witness, if they know where to look and what to expect. The night sky in places that rarely see anything beyond ordinary stars is about to light up in colors that have no business appearing at those latitudes. Green, purple, red. The dancing curtains of light that people travel to the Arctic to see are about to come to them. But the visual spectacle is only part of the story. A solar storm of significant magnitude is also one of the most powerful reminders available to modern civilization of how deeply connected our technological infrastructure is to the behavior of a star 93 million miles away. Power grids, satellites, GPS navigation, radio communications, and even the migration patterns of animals. All of them respond to the invisible forces that a major solar eruption sets in motion across the space between the sun and the Earth. Today, we are going to tell you everything you need to know about this incoming solar storm, what it is, how it forms, what it will do when it arrives, how to watch it safely, and why understanding the sun's behavior matters far more to daily life on Earth than most people ever realize. To understand what is heading toward Earth, you first need to understand what the sun actually is beneath its familiar, seemingly calm surface. The sun is not a solid body burning like a candle or a log fire. It is an enormous sphere of plasma, superheated ionized gas, held together by its own gravity and powered by nuclear fusion reactions in its core that convert hydrogen into helium and release almost incomprehensible amount of energy in the process. Every second, the sun converts approximately 600 million tons of hydrogen into helium, releasing energy equivalent to billions of nuclear weapons simultaneously. That energy works its way outward from the core through successive layers of sun, eventually reaching the surface and radiating outward into space as the light and heat that sustains life on Earth. The sun's magnetic field is generated by the movement of electrically conducting plasma through its interior, a process called the dynamo effect, similar in principle to how electric generators on Earth work. But the sun's magnetic field is vastly more complex and dynamic than anything produced by human technology. It is constantly shifting, twisting, and reorganizing itself as different parts of the sun rotate at different speeds. The equatorial regions rotate faster than the polar regions, winding the magnetic field lines into tighter and tighter configurations over time. When magnetic field lines, in particularly active regions of the sun, become sufficiently stressed and tangled, they can suddenly snap and reorganize in a process called magnetic reconnection. This releases enormous amounts of stored magnetic energy almost instantaneously, the solar equivalent of a compressed spring suddenly releasing. The result can be a solar flare, a sudden intense burst of electromagnetic radiation, including X-rays and ultraviolet light, or a coronal mass ejection, in which a massive bubble of magnetized plasma is expelled from the sun's outer atmosphere and sent traveling through interplanetary space. The coronal mass ejection currently heading toward Earth originated in an active region on the solar surface, where magnetic field complexity had been building for days. When the field lines finally reconnected and released their stored energy, they launched a cloud of plasma containing billions of tons of charged particles outward from the sun at speeds that can range from a few hundred to several thousand kilometers per second. At typical ejection velocities, this cloud takes between 1 and 4 days to travel the 93 million miles separating the sun from the Earth. Space weather forecasters at agencies, including NOAA's Space Weather Prediction Center, track the ejection from the moment of launch, analyze its speed and direction, and confirm that Earth is in its path. When a coronal mass ejection arrives at Earth, it does not simply slam into the planet's surface. The first thing it encounters is something invisible but enormously important: the magnetosphere. The magnetosphere is the region of space surrounding Earth that is dominated by our planet's magnetic field, generated by convection currents in the Earth's liquid iron outer core. Again, The dynamo effect. The magnetic field extends tens of thousands of kilometers into space, deflecting the constant stream of charged particles flowing outward from the sun. This constant stream, called the solar wind, is relatively gentle under normal conditions, and the magnetosphere handles it with ease, channeling the particles around the planet and allowing only a small fraction to enter the atmosphere near the magnetic poles. When a coronal mass ejection arrives, the situation changes dramatically. The ejection carries its own magnetic field, and when that field has a component pointing in the opposite direction to the Earth's magnetic field at the point of contact, the two fields can connect and merge in a process called magnetic reconnection at the magnetopause, the boundary of the magnetosphere. This allows large quantities of charged particles from the ejection to pour into the magnetosphere, dramatically energizing it and causing the geomagnetic storm that all the subsequent effects flow from. The severity of a geomagnetic storm is measured using a scale called the planetary K-index, which runs from 0 to 9. The scale classifies storms into 5 categories: G1 minor, G2 moderate, G3 strong, G4 severe, and G5 extreme. Each step up the scale represents significantly more intense geomagnetic activity, with correspondingly more pronounced effects on both natural phenomena and human technology. The 1989 storm that caused the famous Quebec power blackout was a G5 event. The famous Carrington event of 1859, the most powerful geomagnetic storm in recorded history, which set telegraph wires on fire across North America and Europe, would be classified well beyond even that scale by modern standards. The incoming storm is forecast to reach significant intensity, and even at moderate levels, the effects are worth understanding and preparing for. The most immediately exciting consequence of a significant geomagnetic storm for most people is the aurora, the spectacular light display that results when energetic charged particles from the storm cascade down along magnetic field lines into the upper atmosphere. The physics of aurora production is genuinely elegant. As charged particles spiral along Earth's magnetic field lines and enter the upper atmosphere at the poles, they collide with atoms of oxygen and nitrogen in the thin air at altitudes of roughly 100 to 300 kilometers above the surface. These collisions transfer energy to the atmospheric atoms, exciting their electrons to higher energy states. When those electrons return to their ground state, they release that energy as visible light, and the specific color of light emitted depends on which atmospheric gas is involved and at what altitude the collision occurs. Oxygen at high altitudes, above about 200 kilometers, produces a red aurora that is least commonly seen, requiring the most energetic storms to become visible. Oxygen at lower altitudes, between roughly 100 and 200 kilometers, produces the green aurora that is most familiar from photographs, the iconic curtains and ribbons of emerald light that define the visual identity of the northern and southern lights. Nitrogen produces blues and purples, and the combination of all these colors in sufficiently active display can produce the full spectrum of aurora colors that make strong events so visually overwhelming. Under normal conditions, the aurora is confined to a ring around the magnetic poles called the auroral oval, typically visible only in places like Alaska, northern Canada, Iceland, Norway, Finland, and the equivalent latitudes in the southern hemisphere. But during significant geomagnetic storms, the auroral oval expands dramatically toward the equator. During G3 and stronger events, aurora can become visible across much of the continental United States, across Central Europe, across large parts of Asia, and at equivalent latitudes in the southern hemisphere. During extreme events, aurora has been reported from locations as far south as the Caribbean and northern Mexico. The incoming storm has a potential to push aurora visibility well into mid-latitude regions where most people have never seen it and may never see it again. If you are located anywhere in the higher latitudes of the United States, across Canada, to the United Kingdom, across Scandinavia and northern Europe, or at equivalent southern latitudes, this is an event worth clearing your calendar for. The beauty of the aurora is the visible face of a phenomenon that also has significant and sometimes serious effects on the technological infrastructure that modern civilization depends on. Understanding these effects is important both for appreciating the true scale of what a solar storm represents and for knowing what disruptions to anticipate. Power grids are among the most vulnerable systems. The rapidly fluctuating magnetic fields of a geomagnetic storm induce electrical currents in long conducting structures, particularly the high-voltage transmission lines that carry electricity across countries and continents. These geomagnetically induced currents can overload transformers, cause voltage instability, and in extreme cases trigger widespread power outages. The 1989 Quebec event remains the most dramatic modern example. The entire province lost power for 9 hours as the storm overwhelmed the electrical grid in a matter of seconds. High-voltage transformers damaged by geomagnetically induced currents are expensive, difficult to replace, and in some cases take months to manufacture and install. A Carrington-level event hitting the modern power grid is considered by some infrastructure analysts to be among the most serious natural hazard scenarios facing developed nations. Satellite operations face their own set of challenges during significant storms. The energetic particles in the coronal mass ejection can penetrate satellite solar panels and electronics, causing temporary malfunctions, data errors, or in severe cases permanent hardware damage. The enhanced density of the upper atmosphere during storms, heated and expanded by the influx of energy, increases the aerodynamic drag on satellites in low Earth orbit, causing their orbits to decay faster than normal and requiring operators to make corrective burns to maintain altitude. The large constellation of low-orbit satellites that now provide services ranging from internet connectivity to weather monitoring to military surveillance are all affected to varying degrees. GPS navigation is affected through a different mechanism. The ionosphere, the electrically charged layer of the upper atmosphere, becomes highly disturbed during geomagnetic storms, and GPS signals passing to the disturbed ionosphere experience delays and distortions that can introduce positioning errors. For most civilian users, these errors are minor inconveniences. For precision applications like aircraft navigation, autonomous vehicle operation, and geodetic surveying, they can be operationally significant. Radio communications, particularly high-frequency radio used by aviation, maritime operations, and emergency services, can experience blackouts and interference as the disturbed ionosphere disrupts the propagation of radio waves. The most severe radio blackouts during intense storms can affect communications over wide geographic areas for hours at a time. None of these effects are reasons for alarm during a moderate to strong storm. They are reasons for awareness. For utility operators, satellite operators, aviation authorities, and emergency services to take the standard precautionary measures that space weather forecasts are designed to support. One of the most remarkable and least widely known aspects of geomagnetic storms is their effect on the animal kingdom. Many species use the Earth's magnetic field as a navigational tool, a biological compass built into their physiology over millions of years of evolution. When the magnetic field is disturbed by a solar storm, these species can become disoriented in ways that affect their behavior, migration, and survival. Migratory birds are among the most extensively studied examples. Many species, including various songbirds, raptors, and waterfowl, possess magnetite crystals in their beaks or specialized photoreceptor cells in their eyes that allow them to sense the direction and intensity of the Earth's magnetic field. During geomagnetic storms, this magnetic sensing is disrupted, causing birds to navigate incorrectly. Studies have documented increases in bird disorientation events, unusual migration timing, and radar observations of birds flying in atypical directions during geomagnetically disturbed periods. Marine animals show similar sensitivity. Whales, dolphins, sea turtles, and various fish species use magnetic field sensing for long-distance navigation across ocean basins. Researchers have found statistical correlations between geomagnetic disturbances and whale strandings, events in which whales beach themselves on shores, suggesting that magnetic disorientation may contribute to navigation errors that bring whales into shallow coastal waters. Sea turtle hatchlings, which orient toward the ocean by sensing both light and the magnetic field, can become confused during disturbed periods. Even insects are affected. Honeybees, which use the Earth's magnetic field to orient their waggle dances and navigate between the hive and food sources, show altered behavior during geomagnetic disturbances. Studies have documented increased aggression and reduced foraging efficiency in bee colonies during storm periods. Observations with potential implications for pollination in agricultural regions during major events. These effects are not catastrophic for wildlife populations under normal storm conditions, but they serve as a reminder that the electromagnetic connection between the Sun and Earth is not merely a technological concern. It is embedded in the biology of thousands of species across the planet. If you are in position to witness the aurora during this storm, the experience is one you will not forget. Here is everything you need to know to maximize your chances of seeing it. Location is the single most important factor. You need dark skies, genuine darkness, well away from the light pollution that washes out the night sky above most cities and suburbs. If you live in or near a major metropolitan area, you will likely need to drive at least 30 to 60 minutes into the countryside to escape enough light pollution to see a meaningful display. Higher elevation helps marginally, but is far less important than simply getting away from artificial light. Open horizons are valuable. Aurora often appears low on the horizon, particularly at mid-latitudes, and trees or buildings blocking your northern sky can significantly limit what you see. Timing matters enormously. Aurora activity typically peaks in the hours around local midnight, when your location is on the night side of Earth facing directly into the magnetospheric tail, where storm effects are most intense. The period from roughly 10 in the evening to 2 in the morning local time gives you the best statistical chance of seeing activity. Activity can occur at any hour of darkness, however, and particularly strong events can produce visible aurora at sunset or sunrise. Space weather monitoring tools give you real-time information about storm intensity. NOAA's Space Weather Prediction Center website and associated apps provide current K-index readings and short-term forecasts updated every 3 hours. Several dedicated aurora forecast apps provide push notifications when geomagnetic activity exceeds user-specified thresholds, which means you can sleep until the alert wakes you rather than standing in a field all night waiting. Photography captures aurora far more effectively than the naked eye because camera sensors accumulate light over time through long exposures. If you have a camera capable of manual settings, use the widest aperture available. Set your ISO to between 1600 and 6400 depending on the brightness of the display, and use exposures of between 5 and 25 seconds. A tripod is essential for exposures of this length. Modern smartphone cameras with night mode or astrophotography mode can capture surprisingly good aurora images even without dedicated camera equipment. A solar storm of significant magnitude is, at its core, a reminder that the Earth does not exist in isolation, that our planet is embedded in the dynamic and sometimes violent environment of an active star, and that the magnetic and electromagnetic connections between the Sun and the Earth shape everything from the colors of the night sky to the functioning of our most sophisticated technology to the navigation of animals that have never seen a compass. The aurora that will paint the sky in the coming nights is not just a light show. It is physical evidence of forces on a scale that dwarfs anything human civilization has ever produced. Billions of tons of plasma launched from the surface of a star, crossing 93 million miles of space, and interacting with a magnetic field generated deep inside our planet to create curtains of colored light visible to the naked eye from thousands of miles away from where they are usually seen. Go outside, find dark skies, look north, and remember that you are watching the sun reach out across space and touch the Earth in the most beautiful way it knows how.